This is lecture number 25 of the course AU 203 Statistics and Quality Control, and we have already done sampling of mean and center limit theorem. Today we will extend the sampling distribution idea and the sampling proportion. So we will, after doing this sampling and sampling distribution, we will look into the rules for the calculating the expected value and variance of a random variable, and then we will do the sampling distribution when you're talking about calculating the difference of the two means. So you are actually investigating two different populations, and you are interested in calculating probability related with the difference of the two means. And then we start a concept of population proportion, and then we'll look into the sampling distribution of the population proportion. So if you look at the expected value of random variable to be calculated, expected value of a constant is a constant, and a times x would be a times expected value of x. And if you have a linear function, then you can employ this fact. And if expected value of a random variable you calculate by taking the sum of the values, or if you take the sum and then if you take the expected value and then take the sum, it is actually the same thing. Up to 5 we have already seen that the expected value of a random variable comes out to be the mean value. And from the sampling distribution, if x is a random variable and x bar represents the sample mean, then the expected value of the sample mean is equal to the population mean. So this is number 6 has been added earlier in the properties, because we have completed this sampling distribution of the means. Similarly, we can see that variance of x bar is added here. If x1, x2 are the random variables, then x bar is the mean of the random variables, and the variance of the sample mean would be equal to the variance of the population divided by the sample size. So this is, we have derived it analytically and seen and proved it with some examples as well. So this thing is added, and we already know that the variance of a random variable can be written in an alternate form, where if you are having a data related with expected value with sum of x and sum of x square is given, then you can work out the variance from this alternative formula, and it is common to be used in different problems. Okay, so let's say we have two independent populations, and both populations are normally distributed. It means each population is having a mean mu1 and variance sigma 1 square. So second population is also having a mean mu2 and variance sigma 2 square. So if we calculate the mean of both populations, x1 bar represents the mean of the first population, and x2 bar represents the sample mean of those second population. And each population would have, each sample would have a sample size of n1 and n2. Let's say from these populations, if we take the difference of the mean of these two sampling distributions, so we will be interested in the difference of the sample mean. So x1 is the sample mean for population 1 and x2 bar is the sample mean for population 2. So its mean value would be, can be represented as mu represents the mean value, and here the random variable is the difference of the sample mean, x1 bar minus x2 bar. And which we will not derive, but we will write down the result that the difference of their sample mean would be equal to the difference of their mean for both populations. So that would be the sample mean for population 1, and that would be the sample mean for population 2, and it would be equal to the difference of the population means. So just like the same as if x is your random variable and you are interested in mu x bar, so mu x bar would be the mean of the random variable, and then we see the expected value of the mean of the random variable would be mean of the random variable would be equal to the same as the population mean. So here, if we are talking about two different populations and we are interested in the mean or difference of the mean of the two sampling distributions, it would be equal to the difference of their population mean. And if you see their variance, so their variance is would be the variance of the population 1 plus the variance of the population 2, and that is actually the variance of their sampling mean, which would be equal to, we already have learned from sampling distribution of the mean that the variance would be equal to sigma 1 square over sigma square over n. So for population 1 it would be sigma 1 square over n1, and for population 2 it would be sigma 2 square over n2. So these are the two results which we are directly writing it down. So in order to calculate the probability, as we know that if these two independent populations, so it means there is no dependence, so the both populations carrying random variables which are independent random variables, and their means are mu1 and variance is sigma 1 square, and their sample mean would be x1 bar and x2 bar, and their sample sizes are n1 and n2. So from these populations, the sampling distribution, which represents the probability, would be equal to, from this formula to calculate the z. In the numerator you are dealing with the difference of the sample means, and this is the difference of the population mean, and this is the square root of the their variance. And we can see that is that this z would be a random variable. Another random variable which is normally it is a standard normal distribution representing standard normal distribution, and this would be true if the condition of the central limit theorem applies. So we have already seen that the central limit theorem says that if you have a population which is having any distribution, if you take its sample mean and your sample size is somewhat greater than 20 or 30, some higher values, then your sample mean would also be the from a normal distribution. So since their difference of the sample mean would also be a normal distribution, so we can calculate the corresponding probability from this z value. If either n1 or n2 is fewer than 30, because this is the 30 is then the sampling distribution will still be approximately normal, provided that the population from which the sample is taken is not significantly different from the normal distribution. So this condition of 30 sample size is quite stringent, but even in this smaller than 30 number, it could be 20 or 15. The result works well with this normal distribution when your parent distribution from where the samples have been drawn is not very much different from the normal distribution. So even this condition of central limit theorem works, and the central limit theorem also says that if your sample size is ideally should be greater than 30, but even if it is smaller, one can use the normal distribution if your parent population from which the sample is drawn is not significantly different from the normal distribution. Okay, now let's see the problem, how we can solve such. We are dealing with the difference of the mean values. For example, the television picture tubes of a manufacturer A have a mean life of 6.5 years and a standard deviation of 0.9 years. So television tube manufacturer A has a mean life and standard deviation is given, and while those of manufacturer B have a mean life of 6 years and a standard deviation of 0.8 year. So what do you think about which manufacturer you are going to buy, the manufacturer A or B? As you know, the mean life of A is 6.5 years, which is higher than 6 years. So just if you decide on the basis of the mean, then manufacturer A have a higher mean life than the manufacturer B. But obviously, there is manufacturer A has a higher standard deviation, whereas manufacturer B has somewhat lower standard deviation. Okay, so what is the probability that a random sample of 36 tubes from the manufacturer A will have a mean life that is at least 1 year more than the mean life of the sample of the 49 tubes sample from manufacturer B? So if you keep in mind the sample size here as both are greater than 30, so you can apply the center limit theorem. So whatever the distribution, original distribution is, one can calculate, use the normal standard normal distribution or a z value to calculate the probability in which the difference of the mean is at least 1, or the difference is greater than 1. First step is always look at the sample sizes, and we have learned that they are greater than 30. So center limit theorem applies, and x1 bar we represent the normal random variable, which represents the mean lifetime of a picture tube from a manufacturer A, and we know their sample mean is normally distributed with mean and variance. Similarly, we can write for manufacturer B, x2 bar represents the normal random variable, which denotes the mean life of the television tube from manufacturer B, which is mean life is 6 and the variance is 0.8 square. The question which has been given is the difference of the mean is greater than and equal to 1, because at least means the difference is either the difference of the mean value is either greater than 1 or equal to 1. So this is something we have to work out. So now we are dealing with the difference of the mean values. So difference of the sample mean would become our random variable here. So the mean value of the difference of the sample mean would be equal to the difference of the population mean, as we have already seen in the formula. And similarly, we can work out the variance of the difference of their sample means would be equal to the sum of the variances. So now you look at the variances, it is 0.9 square and 0.8 square, and because of the sample sizes, this resulting variance is different from individual population variances. So because these are different numbers. And you know why I have divided by n1? Because we are not dealing with random variable, we are dealing with the sample mean actually. So one sample mean, we always have a formula for variance would be from sampling distribution, that variance divided by the sample size. So now we can easily calculate the z value. Z value is this difference, and this is a variance, so standard deviation would be the square root of that, and the difference is greater than 1, or z value should be greater than equal to 2.65. So if you calculate from the table the value of z greater than 2.65, so the 0.04 is the probability. So it is very rare is the probability, only 0.4% is the probability that the difference in average mean life of these picture tubes, the difference would be greater than 1. So it means it is more probable that it would be, the difference would be less than 1. So only 0.4% is the probability that the difference is greater than 1, or so you cannot just 0.4% is a very small probability. If it's this probability comes out to be somewhat 2%, 5%, even one can think of that okay, there is a possibility that the difference of the mean life would be greater than 1. So this is how we need to deal the sampling distribution of the difference of the two mean values. Okay, now we come to not the mean values, but we come to another parameter. Parameter is always from a population. So we call it a population proportion, or a percentage of a population that has a particular attribute or a given attribute. So capital P is actually the proportion or the percentage of the population that has a specific attribute. And population means doesn't mean people. Population could be any batch of production or anything, and that would be representing the population proportion. For example, this population proportion could be a percentage of adults who have health insurance. In our country, health insurance is not mandatory, but in several countries in the world, the health insurance is a mandatory part. So, the how many out of the thousand or have health insurance? So this proportion would be representing a population proportion, or the percentage of the cars that are imported. So if let's say 50,000 cars are imported in a year out of 300,000 cars we produce in the country, so that would be the population proportion of attribute, that these are the number of cars that are being imported. Or in a production line, if the percentage of defects in a production, so you are producing let's say 1000 parts, and out of which 5 parts, 7 parts are defective, so that percentage or proportion is representing a population proportion. Or the percentage of women in the labor force. For example, if we compare in Pakistan, it is a small fraction, but it could be a big number in advanced countries. So the population proportion could be any random variable. It could be any number out of the population size. Capital N represents the population size, and X can take any value, any percentage, any number out of the total N. So if you put in the form of the ratio or percentage, that is called as population proportion. Okay, so let's say we have X represents the number of members of a population with this particular attribute out of the population size of N. The just like the same as we already have seen that if X is a random variable and the small x is a value of that random variable. So what you call it a sample proportion, which is a statistic. Population proportion is a parameter because it is something we have taken from the whole population. And sample proportion, we use a cap to represent sample proportion. It means P cap is actually the sample proportion, which is actually the proportion of or the percentage of the item that has been taken from a population and having certain attribute. That would be called as sample proportion. So sample proportion would be a statistic, whereas population parameter, population proportion would be a parameter. For example, if I write like this, sample proportion, so it could be any number from out of the sample size of small n. So we are using small n to represent the sample size and capital N to represent the population size. So where X denotes the number of items or members in the sample that has a particular attribute with the sample size of n taken from a population size of capital N. So that is called as sample proportion. So if you look at the language, we have already learned that mean is a parameter, and we use a Greek letter to represent the parameters, and parameters are always talking about population, whereas the mean of the sample is called a statistic, and statistics is always from a sample taken. So here once you're talking about mean values, you're talking about proportion, then this capital P is a population proportion, which is a parameter, and P cap is actually a estimate of population, and this estimate is coming from a sample. That's why we call it an statistics. So this continues the same notation. We differentiate parameters and statistics. Parameters are always from the population, and statistics is always from a sample. Okay, suppose we have a simple random sample of n observations is taken from a population in which the proportion of success is small p. So small p is just like x is a random variable. When you're talking about its mean value, then x bar is a sample mean and mu is a population mean. So here the particular value of the population proportion is represented by small letter p. So it is just like capital X is a random variable and the value of the random variable is small x. So in the same manner, small p is representing the value of the proportion of success taken from a population, and their failure would be, the probability of success would be p, then the probability of failure would be 1 minus p. It means you are dealing with a simple random sample. It means this random variable has the same feature as the binomial random variable, where you have two possible outcomes: either you have a success or not having a success. So not having a success would be called as failure. If a success proportion is p, then the failure proportion would be 1 minus p. If x is the number of successes in the sample, then this random variable is going to follow a binomial distribution. As you see, this population proportion is 5 out of 1000, or 5 out of 2000, or 7 out of 500. It means all these numbers, random variables, would be some discrete values. So once we are dealing with the discrete values, so we need to look into the binomial distribution, because here you pick a sample and so if x is your random variable, which is a discrete random variable, then we use a normal distribution, and the mean of the normal distribution can be calculated. The formula from n times p, which n is the sample size of the random sample and p is the proportion of the success, and the variance would be np times 1 minus p. So this is the same formula we have deal it earlier, and in short we can write that here a random x is a random variable which is binomially distributed with the sample size is n, and p is its probability of success. So their expected value would be n times p, and the variance of that random variable would be np times 1 minus p, which is the probability of failure. So let the random variable for the proportion of the success in the sample is p cap, which is x over n, where x represents the number of successes out of n trials. And these trials here are the Bernoulli trials. And the mean and variance of the sampling distribution of the proportion, because this is a population sample proportion, which is a statistics, and its expected value, we can say the mean value of the population proportion of that sample would be equal to the expected value of p cap, which is a sample proportion. So from the formula we know expected value of ax would be a times expected value of x. Here a is 1 upon n, so 1 upon n come out of that, and expected value of x, and expected value of x we have already seen np. So n and n cancels out, so expected value of a sample proportion would be the same as equal to the value, its value is equal to the proportion of the success. Similarly, we can work out the variance of this sample proportion, which is sigma square represents the variance, and the subscript p cap represent this is a population proportion. In for variance of x bar, which is the mean value, we used to write sigma square and x bar. Since we are dealing with the sample proportion, so we use the symbol in the subscript to represent that this is the variance of the sample proportion. So it would be equal to variance of x over n, and according to the rules we have seen today, the variance of ax would be a square times the variance of x. So 1 upon n would be 1 upon n square times variance of x. So 1 upon n square, and variance of x we have already seen np 1 minus p, so this n and n cancels out, so p times 1 minus p over n would be the variance of the sample proportion. So the distribution of the sample proportion p cap is actually called the sampling distribution of the proportions. Just like the same as if you have a distribution where you have some random variable x and x bar represent the sampling mean. So here p cap represent the sampling distribution of the proportions. And the once you know the variance, then obviously the standard deviation would be nothing, just the square root of that variance. So if you take the square root, it will give you the standard deviation of the sample proportion. And this is exactly the same picture we have seen for sampling distribution of mean. Let's say we have certain population, and here the population parameters, population characteristics are called the parameters. So small, let's say here they use the small p to represent. We have used capital P. I mean, there is no difference actually, but if you use a capital P, and capital P cap would be your sample proportion, and SRS represents the simple random sample. It means each sample is independent of each other. So and n is the sample size. Let's say for each sample the sample size is same. Then if we have a population and we take different samples, simple random samples from that population, and estimate the sample proportion p cap, and if you see the distribution of the sample proportion, so this sample proportion would be distributed just like the same as symmetrical normal distribution, with the mean value is the same as the probability of success, and its standard deviation would be this. So if you take the variance, then it would be p times 1 minus p over n would be the variance. So in earlier we have seen that if you have a population x, and x bar represent the sample mean, and if you plot those sample mean, then sigma square over n, or sigma over under root n would be the standard deviation, and the population mean would be this its central tendency. So this also follows the population proportion, also follows this behavior when you distribute the distribution of the sample proportion. So sample proportions would be normally distributed with mean and variance. So this is once you have this, so the same normal distribution can be used to calculate the probability associated with sampling proportion. Okay, let's say if you have such a case in which n is large, it means the central limit theorem can apply, and the distribution of the population, distribution of the sample proportion would also be normally distributed. So we can say that the sample proportion is normally distributed with the mean value equal to the probability of success, and p times 1 minus q. 1 minus p is actually q, which sometimes we write q, or sometimes we write 1 minus p, which is the probability of failure, divided by n would be representing the variance. And if we take the square root, then it will be a standard deviation. So for large samples, we can see the distribution of the sample proportion as a normal distribution. And larger the sample size, the better is the approximation. Usually the sample size condition for larger sample to be satisfied with when your sample size and the probability of success is greater than and equal to 10, and the product of the sample size and the probability of failure. So if both these conditions are satisfied, then we can use the normal distribution to predict the probability of the sampling proportion, where the sampling proportion is going to lie, because the sampling proportion itself would be a random variable, because you are choosing randomly from the population. So sample proportion is a statistic. And if you look at different distributions, for example, if you have such a case in which your sample size is 15, which is still less than 9, but if you take the product of the n and p, So 15 into 0.1 would be 1 point, it would be some smaller number. And we can see that this distribution is not exactly normal, but because that lot of area is going outside the normal distribution, but it is going closer if your sample size increases. Let's say if your sample size is 100 and your probability of success is 0.1, then 0.1 multiplied by 100, NP number would be equal to 10. So if it is 10, then your distribution would be considered as a normal distribution. So this thing can be improved. Either you increase the sample size or you increase the probability. We have already seen earlier in your binomial distribution, when your probability of success is 0.5, then you used to have a symmetric distribution. If p is other than 0.5, either smaller than 0.5 or greater than 0.5, then you have asymmetric distribution. So if you calculate half of that number, 15 into 0.5, so it comes out to be 7.5, which is somewhat closer to 10. So we can think it is, even though it is close to normal distribution. So there is always, not necessarily always, these conditions, n greater than 30 or np greater than 10, or this to be satisfied. We need to plot the data, and if data is symmetrical close to normal distribution, so we can use normal distribution to table to estimate the corresponding probabilities. So let's see from this problem how we can calculate. It is known from history that 3% of the part delivered by a manufacturer are faulty. So this is something we know from history, that out of 100, 3 parts are faulty. This manufacturer has supplied us 500 parts, and so 500 parts have been supplied. So we are interested in calculating what is the probability that more than 5% parts are faulty. So here the probability of success, which used to be for the population, is 0.03%, and for that particular sample of size 500, we need to calculate the corresponding probability. So the first thing is P is, we are assuming P is the probability of faulty parts from that manufacturer, and so this is a population parameter, so this is without a cap. And this, the value of that population proportion is 3%, which is 0.03. And let's say we take a sample of 500 parts, so their sample proportion of the faulty parts would be represented by p cap. And as we know, when n is large, which is large number, then the distribution of the sample proportion would be normally distributed with mean this and variance this. So we just substitute the values here. So small p is 0.03, and 1 minus p would be 1 minus 0.03, and 5. So you got these two numbers for your sample proportion. So what you need to estimate that your sample proportion is greater than more than 5% are faulty. So this sample proportion should be greater than 0.05. So what would be that probability? So we need to work out the z value. So p cap would be 0.05, and their mean value for this sample proportion is 0.03, and divided by the standard deviation. So this is the variance. If you take the square root, then it would be its standard deviation. So you end up with 2.621, and you know this z value is represent from the table. You see that only 0.44% is the probability that your from that manufacturer 5% part would be faulty. So it's a very small probability. We can improve this approximation by applying the continuity correction. We have already seen when we are dealing with the discrete random variables, and the normal distribution is a continuous distribution. So converting this discrete random variable into continuous random variable, we need to use the correction factor, and this we have addressed in this lecture of binomial distribution. So here we are not only dealing with this is not 0.005, actually it is 0.05. So that has actually be corrected. This number should be 0.05. So I just correct that number here. Okay, now it is corrected. And you can see that this 0.05, the probability that the sample proportion would be greater than 0.05. 0.05 is, okay, I'm sorry, here I could not make it correct. Here also I need to correct it. Okay, here it has been corrected. Okay, so we see that for this particular population, this sample proportion is greater than 0.05, means 5% part are faulty. So the corresponding Z value is 0.4%. So we need to subtract some value which is 1 upon 2n, because n is a sample size. So this is the 1 upon 2n is the formula for making the correction once you are dealing with the population proportion. We can do the same thing using the binomial numbers, like 3% part means we calculate out of that total. We don't know this, but 5% of 500 we can work out. So in that you need to do that number. Let's say if number comes out to be 25, then 25 plus minus 0.5, it would be 25 minus 0.5 would be 24.5. So instead of 25 you need to use 24.5. So here instead of 0.05 you need to take 0.049 after making the correction. So once you employ this correction, then your Z value would be not 2.62 but 2.49. So the corresponding probability would be 0.6%. So there is a slight difference, but still there is a very small probability that from that manufacturer 5% part would be faulty if that manufacturer supplies 500 parts. And keep in mind this probability would going to change if the sample size is changing. So this in this population proportion, and we will see it in the later part of the different other lectures as well, to calculate the sample sizes. So here if you change the sample size, then the probability is going to change. So let's say if it is 100 parts, and if you calculate the same problem with n equal to 100, so you end up with different numbers. So it means for smaller samples, if the probability of finding it would be different. Or if these historic probability or population parameters like 3%, if it is different, if it is 2%, then obviously your probability would be different. So depending upon those numbers we can calculate the probability, and this usually happens in most of the problems, practical problems in which you are dealing with the population proportion. And we will use the control charts for the population proportion as well in the later lectures. So here I stop this, and you can do the same thing on the software. Probably in the next lecture I will show you using the software as well. So I stop this lecture today.